tilted or not, the variation is in y, but the direction is in x, and hence u dot grad u is 0. That is to say, the grad is only in the y direction, that's where the variation is. But if you take u, but this is, the flow is only in the x direction. We can do the computation, but you'll see this is 0. This is what makes those analytic forms so easy to find. There is no nonlinear term. Right? Here you take, well, anyway, you can easily do that. The Laplacian of a linear function is also 0. So yes, laminar Couette flow is an equilibrium between the nonlinear terms, the advective terms, and the viscous terms. But it's a trivial one. It's 0 equals 0 plus 0. And that's true if you tilt it as well. If you tilt it as well, then you'll still have that. The variation is in y, but the flow is perpendicular to that. Okay? So again, you have 0. The sum of these two is 0 because each individual one is 0. So you can see from this right away that what you have in this so-called laminar region is not laminar Couette flow. It's got a viscous term, and it's got a nonlinear term that are equal and opposite. So this one should be laminar in quotes, and this one in fact should be turbulent in quotes. Many people when they give this seminar have said, wait a minute, where's your Kolmogorov spectrum? This isn't turbulence. Okay, it's not turbulence, it's chaotic, it's irregular, it's all those things. Some people won't call this turbulence. You know, it's filled with those little streaks, it's filled with structures. Okay, it's not sure. So we can put this in quotes, call this quasi-turbulent, quasi-laminar, quasi-turbulent.
It use your span-wise direction normal to the 24 degrees.
That's right. It's not a span-wise direction, it's the direction of, okay, this is where you have...
Across the large...
That's right. Across the large... You have these bands, and the turbulent region, laminar, turbulent, laminar, that's the z direction. Turbulent, laminar is z. And indeed, turbulent, laminar, turbulent. You would see the same if you actually used the span-wise direction, but because there would be a component, it would be oblique like that. But it's more clean to look at it that way. And, yeah, this is, let's see, I could say, yes. Okay, I said I would answer the question about what maintains the turbulent, the turbulent laminar pattern, and so here is what I have to say about it. It's not that. We have an equilibrium, indeed, between advection and viscosity. And the viscosity turns out to be mostly dy squared. It's like boundary layer theory. The variation perpendicular to the wall is much more important than the variation parallel. Right. So we have that. Then in the quasi-laminar region, u dot grad u can be mostly approximated as the advection by the base flow. This is the base flow, this is the laminar flow, and it's advecting whatever structures it is you have. So this somewhat complicated, this thing that ought to have, okay, we're only looking in the direction parallel to the bands. There should be 3 components of this, because U has 3 components, but in fact, the only one that matters is this one. It turns out. You just compare them quantitatively. So what you find is that the equilibrium between nonlinear and viscous terms is actually like this. And this is, say, the advection of U. U is those red and blue patches, this deviation from laminar flow. U is, something has to maintain these red and blue patches, keep them from, a fluid likes to diffuse and, get rid of all of its features, right? So something has to maintain it, and here's what's maintaining it. You have turbulence being brought by the base flow to this region, and turbulence being brought below to this region here, and that is what's maintaining the curvature. Curvature is what viscosity doesn't like. Viscosity wants to smooth that out and make it straight. So something has to be feeding it, and what feeds it is the turbulence. But this is not a closed picture. That's why I say it's only a vague idea about mechanism. It's like the other. Nobody's saying what makes the turbulence. Given that you have turbulence here, you will feed the curvature in the quasi-laminar region and maintain it away from laminarity, meaning you maintain this curvature. But it's just like this supposed model here. It's not complete because it's assuming turbulence. It's assuming the F. And so assuming the turbulence there, it maintains that quasi-laminar region. This shows that there are other wavelengths possible. This space is angle and Reynolds number. No, I just said wavelengths, but yes, it will show wavelengths, but it will mostly show angles. These are the different angles, and this is Reynolds numbers. So numerically, we produced patterns at all of these different angles here for all these different Reynolds numbers. These are the localized states that I mentioned where they don't care what wavelength they have, and that happened at the lowest Reynolds number. And then we had a wavelength of 60 and wavelength of 40. Remember when it lost one of the bands? Anyway, you can get lots of different angles. Experimentally, you cannot. But this is just like every other situation. Remember how many times I've drawn this picture. I've drawn convection rolls like this, and I've said we have that, and we don't have this experimentally, and we don't have this, because this is the one that has the lowest threshold. But numerically, or theoretically, we are perfectly allowed to impose a periodic domain here and see what happens. And we can measure the properties of convection that's like this, even though the system will not choose to do this. Or we can measure the properties of convection like this, even though the system will not choose to do this. And so too, we can produce all these different angles. The system will not do this, even though these states exist, because, most likely, but just the same reason they are unstable to transition to this. If you give it the freedom to choose its angle, which you do in a very big domain, it will prefer to have an angle that's about like this, that's in the 24-degree range. Sometimes patterns up to 40 degrees have been observed experimentally. But we, numerically or theoretically, do not have to restrict ourselves to stable things. We can study unstable things by forcing them. Anyway, you see there's a big range, and here are some pictures of the patterns that we get at different angles and different wavelengths. The maximum angle that we got was 66 degrees, the minimum one was 15 degrees, and the minimum wavelength we got was 35, and the maximum wavelength we got was 65. And that is all I have to say about this now, so we should take a break, and I will go on with the story later. Okay, so 10-15 minute break.